here are a few things I was wanting to do in class, but we ran out of time. So this question asks us to find the horizontal asymptotes of f of x equals, and then we have this piecewise function here. So notice here that it could be asymptote or asymptotes. And so in this case, there's going to be two, because as we look at the left side of the graph, we use this equation. But as we look at the right side of the graph, we use this equation. So to find the horizontal asymptotes, first I'm going to look at the limit as x approaches negative infinity. And as x approaches negative infinity, oh, I've got my signs backwards here in my problem. Let me fix that really quickly. That should be a less than sign right there. So as x approaches negative infinity, we're going to be using this top equation because that's where x is less than 0. So the limit as x approaches negative infinity of f of x, I'm going to get whenever I do the limit as x approaches negative infinity of x minus 5 over x squared minus 3x. And I'm just going to kind of shortcut this here. Bobo-Botno ECC tells me that this is bigger on the bottom, which means my limit is going to be 0. Therefore, f of x has a horizontal asymptote at y equals 0. Make sure right here that you give the equation of that asymptote. It has to be y equals 0. Make sure you don't put x equals, because x would be a vertical line. It has to be that y equals 0. Now, this is the horizontal asymptote to the left. A graph can have different ones from the left and the right. For example, those logistic functions that we looked at the other day, they looked something like this. So they had a different horizontal asymptote on the left than they did on the right. So we also have to look at the limit as x approaches infinity of f of x. And in this case, we're looking at that bottom function. So limit as x approaches infinity of e to the x minus 3 over 2e to the x plus x. So this, we're going to use Bobo-Botno here as well, but it's a little bit more confusing because we don't have x to a certain power. We have e to the x. And so basically what we need to know here is e to the x is always going to be bigger than really x to any other power. So if we see an e to the x, that exponential is going to grow a lot faster than any x. So whenever we do this problem, you can think of like dividing all of these by e to the x if you want. And if you think of that, then you have 1 minus 3 over e to the x over 2 plus x over e to the x. So this we know would be 0 because it's a number over something that has a variable. Here, this is also going to be 0 because the e to the x is much larger than the x on the top. So in this case, we're just going to get 1/2. You really can just do this like Bobo-Botno as well, because you have a coefficient of 1 in front of that e to the x. E to the x is a higher exponent than this x over here, so you just have more or less exponents the same, divide coefficients. This is sort of how you can think of it for that problem. So we would say, therefore, f of x also has a horizontal asymptote at y equals 1/2. So that right side, we have a horizontal asymptote that y equals 1/2. Okay, this next example I want us to look at, it says the amount of cars produced by a manufacturing plant is given by the equation C of t equals 23 times t plus 1 times 2t plus 7, where C of t is measured in numbers of cars and t is measured in weeks. According to this model, is there a time t for 0 to 5 weeks where 2,000 cars had been produced? Justify your answer. So here we could try to figure out when C of t is 2,000. We could do something like this. 2,000 equals 23 times t plus 1 times 2t plus 7. But this is calculator inactive. That's going to be a big number, possibly necessary for us to do quadratic formula, and it's going to be nearly impossible to do without a calculator, and if not impossible, at least takes way too long for us to spend that time. So if you look at the question again, according to the model, is there a time t between 0 to 5 where we have 2,000 cars that have been produced? We don't have to tell what it is, we just have to figure out if there is one. So we can use the intermediate value theorem for this. So if we find C of 0, and this is a continuous function, so it will apply. If we find C of 0, we'll have 23 times 0 plus 1 times 2 times 0 plus 7. And so that's going to be 23 times 1 times, this is going to be 0 plus 7, so 7. So we've got 23 times 7, and 23 times 7 is going to give us, 161. So 161 cars. So now we need to see C of 5. And for C of 5, we're going to have 23 times 5 plus 1 times 2 times 5 plus 7. And that gives me 23 times 6 times 17. So let's see. For the sake of time here, I am going to use the calculator. I think that cut off. I'm not really sure how far I had gone in that problem, but here's the answer in case you need to look at it. Okay, here's our next example that I wanted us to do. We have this function, and we need to tell on which intervals this function is continuous. So, we basically need to find all the discontinuities so that we can make sure they're not in any of these here. So, unit circle. I'm going to go ahead and draw it here. And so, this is the point 1, 0. This is the point 0, 1. This is the point negative 1, 0. And this is the point 0, negative 1. And so for this, first we're looking at sine of pi over 2. So sine of pi over 2 is right here. And sine is our y-coordinate. So sine of pi over 2 would be 1. Then I also have to look at tangent of pi over 2. So tangent of pi over 2. That would be sine over cosine. So sine would be 1, and cosine is 0, so this does not exist. So we definitely have a discontinuity at pi over 2. Okay. Tangent has discontinuities. So we need to make sure that we list any discontinuities for tangent that would be between pi over 2 and 3 pi over 2. And as I said a minute ago, tangent is sine over cosine. So if cosine is 0, then that means we have a discontinuity at that point. So that is going to occur at one of these 4 locations here. So tangent at pi over 2, we've already found that it's undefined, so there's definitely a discontinuity there. At pi, we would have 0 over negative 1. That just equals 0, so it's defined at that point. At 3 pi over 2, we would have negative 1 over 0. So tangent of 3 pi over 2 would equal negative 1 over 0. So we would also have a discontinuity at 3 pi over 2. Okay, so we have a discontinuity there. Then we skip down here to cotangent. We already know that it's going to be discontinuous at 3 pi over 2 because tangent was undefined at that point. So we don't need to necessarily check 3 pi over 2 here. We need to think of cotangent. Cotangent is cosine over sine. So since cotangent is cosine over sine, we are looking on the rest of the unit circle for where, well, up to 3 pi, for where cosine over sine would be undefined. So we are at 3 pi over 2. At 2 pi, we would have cosine over sine would be 1 over 0. So cotangent of 2 pi, cosine over sine there is 1 over 0. So we would have a discontinuity at 2 pi. And then at, I guess this would be 5 pi over 2, we would have a discontinuity, we would not have a discontinuity there, we'd have 0 over 1. We would have a discontinuity at 3 pi, because we would have negative 1 over 0, so at 3 pi would also be a discontinuity. So any range that includes these is going to be a problem. If we look at pi over 2, it might be helpful if you look at your answer choices. Everything has a denominator of 4, more or less. So if we got everything to have a denominator of 4, then we're looking at 2 pi over 4. That falls into this range right here. It also falls into this range, so both of those are out. 3 pi over 2, if we got common denominators here with all those 4s, that gives us 6 pi over 4, and that falls in this range, so that one is out. And 2 pi, that's like 2 pi over 1, so we'd have to multiply by 4 on top and bottom, and that would give us 8 pi over 4, which is not in this last range, so that's good. And then the last one, that's like 3 pi, so we'd have to multiply by 4 on top and bottom. That would give us 12 pi over 4, which is also not in this range. So D would be our answer here. Okay. Here are some problems that were highly missed from the progress check. So we're going to look at these and see how we can fix these. Feel free to skip ahead in the video if you already got one of these right and know what to do. For this question, it says let f of x be the function given by f of x, and it gives it there, on which of the following open intervals is f continuous. So really we need to know where the discontinuities are. Discontinuities come from the denominator. So we would say anything that makes that denominator 0 would give us a discontinuity. So x squared minus 3 could be 0, or x plus 0.5 could be 0. And we know here that's just x equals negative 0.5. And then here we've got the 3 has to be moved to the other side. We got x squared equals 3. And then we must square root both sides. So that gives us x equals plus or minus the square root of 3. And so we don't know exactly what plus or minus square root of 3 is, but I do know the square root of 1 is 1 and the square root of 4 is 2. So this is some number between 1 and 2. So let's, if we estimate it at plus or minus 1.5, that'll do well enough over here because you can see we have all whole numbers for our answers. So between negative 2 and 1, negative 5 falls on that interval. So A is out. Between negative 1 and 0, negative 0.5 falls on that interval. So B is out. Between 0 and 1, we don't have any discontinuities. So C is going to be our answer. If you check 1 and 2, positive 1.5 falls on that interval. So D is also out. So C is the only interval on which this function would be continuous. Okay. Not too many people miss this one, but I just wanted to remind you of a function on your calculator. This one is a calculator active question. So let me get the calculator open here. So for this one, you want to know for what values of B f is continuous. So it must be continuous at 2, so you would plug in 2 for x. So you would have e to the b times 2 has to equal 1.5 times 2 plus b. And so you've got e to the 2b equals 3 plus b. And that's your equation that you're dealing with there. That is not an equation that we can solve by hand, or at least I don't know how. So what we'll do here is we're going to use our calculator for that, and we're going to use the solve feature. So if you go to F2, you're going to pick number 1, which says solve. You're going to type in the equation. So you've got e to the, I'm going to use the x instead because it's easier to type, to the 2x equals 3 plus x. And then you have to put a comma and an x after the equation so it knows what variable to solve for. And whenever we do that, it's going to take it just a little while to solve this. But we get negative 0.6469 or negative 2.99751. And you can see that is answer choice D. So that's the one that you're going to choose. Okay, for number 5, it tells us f is a continuous function on the interval negative 1 to 3 and is not continuous on the interval negative 1 to 3 whenever we have the or equal to signs here. Of the following, which could not be an expression for f of x? So this tells us here that the discontinuities for this have to be either at negative 1 or at 3. So whenever we look at our answer choices, I look at A, and this has a discontinuity at x equals 3. So it's a possibility that it could meet these criteria. It could be continuous from negative 1 to 3, but it's not continuous here because of the 3. So A is out. For B, my interval here is at x equals negative 1. So that's where I have discontinuity there. Same thing. That one's out. This one is discontinuous at both x equals negative 1 and x equals 3, but would be continuous in between, so that one's out. C is just a polynomial. This is just a quadratic, and quadratics are continuous everywhere. They don't have any discontinuities at all. So this is the one that would not be true because it would have to be continuous on the interval from -1 less than or equal to x less than or equal to 3. So C is your answer for that problem. For number 6, we have a piecewise function here, and it says let g be the function defined above where k is a constant. For what value of k is g continuous at -3? So you can see here that this is one of those piecewise functions where really this right here is our function. We use it everywhere except x equals -3. So k is just a dot to fill in that value. So what we would do here is we need to find the limit as x approaches -3 of x squared minus 9 over 4x plus 12. And whenever we do that, we'll do the limit as x approaches -3. We will factor the top into x plus 3, x minus 3. And the bottom, we can just factor out a 4. So we'll have 4 times x plus 3. And these x plus 3's right here will cancel. So if we plug in -3, we have -3 minus 3 over 4. And that will give us -6 over 4, which gives us -3 halves. So that is the limit of this function. We have a hole in the graph at that point. So if we make that k value -3 halves, then that'll fill in that hole in the graph. So B is our answer here. Okay. For number 8, the function h is defined by h of x equals x squared minus 7 over x minus 3. Which of the following statements must be true? So whenever we look at what we've got here, we can see all of these are looking at the limits at 3 from the left and the right, and we have infinite limits here. So we're going to have to make a chart on this one. So if we're going to approach 3 from the left like we see right here, then 3 from the left we could use values like 0, 1, 2, 3. So if we plug in 0, we're going to get -7 over -3, so 7/3, or I could make that 2.3 repeating. If I plug in 1, I'm going to have 1 minus 7 over 1 minus 3, and that is going to give me -6 over -2, which is going to give me 3. If I plug in 2, I'm going to have 2 squared minus 7 over 2 squared minus 3. And so I will get 4 minus 7, which will give me -3 over 4 minus 3, which is going to give me 1. So I get -3. Then, if I look, I can see I was increasing and then I start to decrease. So I really am not quite sure what's happening here. So I really need to try like 2.5 or 2.5. So 2.5 minus, or 2. Let's see. Actually, we might have to use fractions for this. We can't do that. Let's do 5 halves squared minus 7 over 5 halves. Let's see, is that squared? 5 halves not squared. Oh, I've messed up. Here. This is not 2 squared. This is just a 2. So this would be -1, which would give us a +3. So still, we're kind of stalling out. We really need to check this 5 halves. So we'll have 5 halves minus 3. So we'll have 25 over 4 minus, I'm going to go ahead and make this 28 over 4 so I can subtract those. And here, this is not squared, it's just 5 halves. So this is 5 over 2 minus 6 over 2. And so that is going to give me -3/4 over negative 1/2. Dividing fractions is easy as pie. Flip the second and multiply. So I'm going to have negative 3/4 times negative 2/1. And that is going to give me 6/4, which is 3/2. So you can see the value decreases here again. So you might need to check another point there. For the sake of time, I'm going to tell you that it's going to be decreasing. So that happens. From the right, you would do the same thing, but you're going to make the chart with the positive numbers. So, for example, for that chart, we might start with 5, and then 5 squared. So you got 25 minus 7 over 5 minus 3 is going to give you 25 minus 7 is going to be, let's see, 25 minus 7 is going to give you 18 over 2, which will give you 9. 4, you're going to have 16 minus 7 over 4 minus 3, which is going to give you 9 over 1, so also 9. So here you've got to check maybe like a 7/2, which is 3.5. So you would go through and check that. So got 7/2 squared minus 7 over 7/2 minus 3. So that's going to be 49 over 4 minus, I'm going to go ahead and make this 28 over 4 over 7/2 minus 6/2. And so you've got 49 minus 28 is going to give us 21 over 4 over 1/2. So that's going to give me 21 over 4 times 2 over 1, which is going to give me 42 over 4, or 21 over 2, which is 10.5, which is an increase. So we see this is increasing here. So C is our answer. Not my favorite problem. Okay. For 11, we have the function f of x equals 2x plus 3 over x plus 1. Which of the following statements are true? So the first says something about the horizontal asymptote. So it says the graph of f has a horizontal asymptote at y equals 2 because the limit as x approaches infinity of f of x equals 2. So if we did this limit here, we can do Bobo-Botno. We've got exponents are the same, divide coefficients. There is a 1 right here. So 2 over 1 equals 2. This is correct. Number 2 says the graph has a horizontal asymptote at y equals 2 because the limit as x approaches negative infinity of f of x equals 2. Whenever you just have polynomial functions, right, or rational polynomial functions like this, there's no square roots involved. It does not matter whether you approach positive or negative infinity. You get the same value. So this second one is also true. And then the last one says the graph of f has a vertical asymptote at x equals -1 because the limit as x approaches -1 from the right of f of x equals positive infinity. So I can tell here that this has a vertical asymptote. That is a true statement. What I need to know is whether or not it actually does approach positive infinity. So if I make myself a chart as I approach -1 from the right, I could start at 1, 2 times 1 plus 3 over 1 plus 1 is going to give me 5 over 2, so 2.5. If I plug in 0, I've got 2 times 0 plus 3 over 0 plus 1. And for that, I'm going to get 3 over 1, which is 3. I can't plug in 1. I could try maybe like 1/2. 2 times 1/2 plus 3 over 1/2 plus 1. That's going to give me 4 over 1/2 plus 1 is 3/2. And dividing fractions is easy as pie. Flip the second and multiply, which is going to give me 8 over 3, or 2.6 repeating. I can't try a -1, but I could try a -1/2. So for -1/2, I'd have 2 times -1/2 plus 3 over -1/2 plus 1. And so this is going to give me -1 plus 3 over 1/2. So that is 2 divided by 1/2. And dividing fractions is easy as pie. Flip the second and multiply, and you'll get 4. So you can feel reasonably assured that this is increasing. So that third one is correct also. So D is the correct answer. Okay. I put that one on there twice. I do not know if that was supposed to be number 11 or number 12. I'll look at that in a second. For 13, this one is a tricky one that we haven't really seen much before. I noticed that 5 of you put y equals 3/8 because you were doing Bobo Botno eats CC. And so this it looks like it is a Bobo Botno eats DC problem. You're looking at horizontal asymptote. The thing that I have probably not told you well enough, and hopefully you're getting now as you watch this video, is that e to the x is a higher exponent than x to any number. So that e to the x we're going to count as our highest exponent. So that means that this one is actually bigger on the bottom, and whenever we have a function that's bigger on the bottom, then 0 is our horizontal asymptote for that. So e to the x is a higher exponent than x to any power there. So even if it's x to 1,000 or x to 1,000,000, e to the x still sort of trumps that. So A should be your answer here. Okay, for 14, it tells us let f be a function such that f of 5 is less than 6, less than f of 7. Which of the following statements provides sufficient additional information to conclude that there is a value x equals c in the interval 5 to 7 such that f of c equals 6. So what we're looking at here is f of 5 and f of 7, those are our y values. 6 is somewhere between the y values here. And we want to conclude that there's some c where f equals 6. If you think of the graph, you've got 5 here, 7 here, f of 5 is here, f of 7 is here, and we know 6 is somewhere in between them. So if we've got 5 f of 5 and 7 f of 7, we want to know if we'll ever have to have a point there that is that has a y value of 6. So this is the intermediate value theorem. And so we already have all the conditions you need for intermediate value theorem. We know that 6 is between our y values. We also know that we're looking on the interval from 5 to 7. So what we're missing here is that f is continuous, because intermediate value theorem does not work if f is not continuous. So that is the condition that we must have. Answer choice D looks a little like it should be correct, because it's, and notice that 5 of you chose it. Everybody who picked the wrong answer picked this. It says there is a value x equals c in the interval 5 to 7 such that the limit as x approaches c of f of x equals 6. So if this is continuous, then this is true. But only if it's continuous, because if I have a function, it could be a piecewise function, and it could look like this, could look like that, and then so my limit does not exist right there. It's never 6 unless I know that it's continuous. While this is a conclusion you can make if it's continuous, you have to know it's continuous first to make that conclusion. So C is the correct answer here. Okay, and those are all the ones that were highly missed. So if you have any other questions, I will be available during lunch tomorrow, so you can come and